This is lesson 28, in which we'll discuss problem-solving techniques. One of the reasons we learn mathematics is to be able to help us solve problems, whether they're small problems of personal nature or giant-sized problems that involve governments, businesses, or what have you. The fact is that mathematics, because we can use it to model situations, both as numbers or with graphs or with charts, we use mathematics to solve problems. There are various courses you can take on methods of problem solving. The purpose of this lesson is just to introduce you to a couple of methods of looking at fairly simple problems that use some mathematics and that allow you to see that there is no one right way to solve a problem. We'll look at, like I said, a few different problems, and we'll see how we can use a method to solve that problem. The first problem involves a farmer. So even if you live in New York City or Chicago, you can imagine a farmer. The farmer has 100 animals. Some of those animals are cows. The rest of the animals are chickens. Altogether, the 100 animals have a total of 372 legs. The question is, how many of each type of animal are there? Well, we could do this by guessing. We certainly won't do it that way. We could also do this using algebra, but this is not an algebra course, and we certainly will not do it that way. We will try to do it in an organized fashion using a chart. So again, let's take a look at the problem. Once again, we have 100 animals. Some are cows, some are chickens. They have 372 legs. What are we going to do to find this out without playing the guessing game? Well, as I said, we'll use a chart. And here's the chart. We have a number of columns. One marked cows, one marked cow legs, a third column marked chickens, the next one chicken legs, and finally total legs. We know that the number of cows plus the number of chickens must equal 100, and the total number of legs must be 372. So what we start off with is, let's take a look at if all the animals were cows. 100 cows, each cow has 4 legs. That would be 400 legs. With 100 cows, there'd be no chickens, since the number of chickens plus the number of cows must equal 100. And the number of chicken legs, therefore, is 0, and the total is 400. Obviously, this is too much. But let's take a look what happens if we have no cows and all 100 of the animals are chickens. So we see that with 0 cows, 0 cow legs, 100 chickens, each with 2 legs, 200 chicken legs, there's a total of 200 legs. That's too small. So someplace between this, we have a combination that will give us 372 legs. But at least we have someplace to work with. And this chart should be very helpful in terms of getting us fairly quickly to the solution. The next step is, let's take the halfway point. 50 cows, 50 chickens. Okay? 50 cows must have 200 legs. 50 chickens have 100 legs. Altogether, 300 legs. 300 is too few. We need 372, which means we need to probably add more cows. Of course, when we had 100 cows, we had 400 legs. When we had 100 chickens, we had only 200 legs. So we try 60. And the next line shows what happens if you have 60 cows and, of course, 40 chickens. 60 cows would have 240 legs, 40 chickens, 80 legs, altogether 320. Still too few legs. We need more cows. How many more? Well, one of the things we could do at this point in time is to analyze what we gain when we add a cow. Obviously, when we add a cow, we lose a chicken, since the sum of the animals must equal 100. So notice what we have here is 61 cows, 39 chickens, total of 100 animals. 61 times 4, 244. So we've gained 4 cow legs by adding 1 cow. Well, that makes a great deal of sense. We have now 39 chickens with 78 legs, so we've lost 2 chicken legs. Well, that makes sense because we've lost 1 chicken and each chicken has 2 legs. Our net gain is 2 legs. We've gained 4 cow legs but lost 2 chicken legs, and therefore went from 320 to 322 legs. The question is now, we want to get up to 372. Every time we add a cow, we add 2 legs. So what's the difference between 372, 322? The difference is 50, a little subtraction problem. And now the question is, how many times do we have to add 2 legs to get those 50 additional legs? Well, obviously we divide by 2, and 50 divided by 2 is 25. So we need 25 more cows. Well, we had 61 cows. 25 plus 61 would be 86 cows. And as you can see, 86 cows would give us 344 legs, that is cow legs, and the 14 chickens would give us 28 legs, a total of 100 animals and a total of 372 legs. Using the chart, we did not have to guess. We were in organized fashion, and one of the most important things in problem solving is organizing your procedure so that you don't skip over something, you don't miss something. And here, once we got far enough, we were able to analyze numerically what happened every time we added a cow or took away a chicken. And then we were able to, using very basic arithmetic, subtraction and division, determine exactly how many cows there were. Now, even if you are a farmer, you probably don't care about how many cows, how many chickens, and combination like this. The purpose of this problem was not that it's a real problem, something we should be concerned about. The idea is it's a problem that demonstrates the use of an organized problem-solving technique. Another technique that's commonly used in solving problems is to make the problem simpler, make it smaller. And here's an example of that kind of problem. You have a school, and the school has exactly 1,000 students. It also has exactly 1,000 student lockers. And every year on the first day of school, all the students line up in alphabetical order. And student number 1, which is probably, the first Amy Arkwright or something like that, or Amy Aardvark, I guess. Her first name begins with A, and her last name begins with AA. Amy Aardvark walks through and opens up all the lockers, and then she goes on to wherever she goes. The second student, alphabetically, student number 2, walks through and closes all the lockers that are divisible by his or her number by 2. That is, all the even-numbered lockers are now closed. The odds are still open. The question is, if this continues so that the third student goes through and changes the position of all the locker doors where the lockers are numbered, a number that's a multiple of 3, and student 4 does the same thing, changes the position. An open locker is closed, a closed locker is opened. For all the lockers where the number is divisible by 4, by the time the 1,000th student goes through, which lockers will be open, which lockers will be closed? Well, that's a heck of a problem. Let's make it smaller. Let's take the first 10 lockers. Make believe this was a small rural school that only had 10 students and 10 lockers. And then once we get an opportunity to look at what happens after the 10 students have walked through, we may be able to generalize and make create an answer for a problem, the larger problem, with 1,000 students and 1,000 lockers. Well, here we can see what happens after the first 3 students have gone through. Student number 1, we notice we have 10 lockers indicated 1 through 10, and after student number 1 has passed through, they're all open, the O standing for open. Student number 2 walks through and closes lockers 2, 4, 6, 8, and 10. The odd-numbered lockers remain open. Student number 3 closes locker 3, opens locker 6, and closes locker 9, because 3, 6, and 9 are all divisible by 3. What I'd like you to do is, at this point in time, to copy down that list of locker numbers 1 through 10 and the results after the first 3 students walk through. And then what I'd like you to do is complete the list for students 4, 5, 6, 7, 8, 9, and 10. And when you've gotten that done, come on back, we'll take a look what happens, and we'll see if we can figure out which lockers remain open after the students have marched through. Stop the tape and work that problem, please. Okay, here we see the results that you should have gotten. Student 4, remember, changes the situation for the doors of the lockers that are divisible by 4. So he or she opens locker 4 and opens locker 8, and those are the only lockers that are touched by student 4. Student 5 comes in and can only change the doors on locker 5 and 10. So locker 5 door is closed, locker 10 door is opened. Student 6 can only affect one locker, locker number 6, because in the numbers 1 through 10, 6 is the only number that has 6 as a factor. And of course, since 6 was opened, student 6 closes locker number 6. Similarly, student 7 closes locker number 7. Student 8 closes locker 8. Student 9 comes through, and since locker 9 had been closed ever since student 3, I guess, closed it, then basically student 9 opened locker 9. Student 10 closes locker 10. If we look on that last line, we can see what has happened after the 10 students have marched through with this procedure. Let's see. Which lockers are open? 1, 4, and 9. Now, 1, 4, and 9. Do you see something common about those three numbers? If you wanted to describe those three numbers, what might you say? You wouldn't say they're even because 1 and 9 are not even. You wouldn't even say they're prime because 1 is not prime. 4 and 9 are composite numbers. What adjective might you use to describe these three numbers as opposed to the other numbers 2, 3, 5, 6, 7, 8, and 10? Well, hopefully you remember our discussion of exponents and the discussion of square numbers. 1 is 1 squared, 4 is 2 squared, 9 is 3 squared. These three numbers are the three square numbers from 1 through 10. Now, why is that true? Why are the square numbers the ones with the locker door still open? I want you to think back to lesson 1. Seems like a long time ago. In lesson 1, we looked at rectangular arrays to represent the multiplication facts for various numbers. We looked at 12, and we saw that 12 could be shown as 1 times 12, 2 times 6, or 3 times 4. We looked at 9. We saw that 9 could be done as 1 times 9, but also as 3 times 3. 9 was a square number. The rectangular representation of 3 times 3 was a square, a very special rectangle. Now, think about that. The square numbers have one set of factors that are the same. That is, the factors of 9 include 3, 1, 3, and 9. So we have 1 times 9 is 9, and 3 times 3. So there are only 3 factors. The number 8 has 1 times 8 and 2 times 4, therefore 4 different factors. Therefore, 4 students, student 1, 2, 4, and 8, will change the position of door 8. 1 will open it, 2 will close it, 4 will open it, and 8 will close it. So all non-square numbers will have an even number of factors. And therefore, an even number of students will affect the position of that locker's door. And therefore, half of them will open the locker, the other half will close it, and the last student to touch that locker door, which will be the student whose number is the same as the locker number, will close the door. Square numbers have an odd number of factors. For example, 16. 1 times 16, 2 times 8, 4 times 4. And therefore, 1, 2, 4, 8, and 16 are factors of 16. So therefore, an odd number, 5 factors. 3 of those students, 1, 4, and 16, will open the lockers. 2 of those students, 2 and 8, will close the lockers. And therefore, when 16 is finished, the locker is open. So the answer is, among the 1,000 lockers in the original problem, the square numbers lockers, 1, 4, 9, 16, 25, 36, etc., will be open, and all the other non-square numbers will be closed. Now think about that problem. Not only do we show a method of making the problem simpler to see, we also use the notion of multiples and factors. We talked about square numbers and rectangular arrays, and square arrays. So quite a few things that we've talked about previously had to be known to be able to solve this problem. The knowledge of various mathematical facts, concepts, and methods is very helpful in problem solving. Okay, let's consider another problem. This is a problem that really isn't as mathematical as it is the ability to visualize. We have a cake. The cake must be cut using exactly 3 cuts. It has to be cut into 8 equal pieces. Hopefully, many of you have not seen this problem before, because I'd like you to stop and think about how you would cut this cake into 8 equal pieces using only 3 cuts. Stop the tape and consider your answer to that problem now, please. Many people say it's impossible. They try to cut the cake and cut it again, and you wind up cutting it either into unequal pieces or not into 8 pieces. That's because you're limiting your visualization to making cuts from the top down. Imagine cutting the cake halfway from the top down, then rotating the cake 90 degrees, we know what that means, and cutting it again from the top down. You now have divided the cake into 4 equal pieces. The third cut is not done from the top down, it's done halfway up the cake, across the cake, and as you can see in the cuts demonstrated in this graphic, you would cut the cake into 8 equal pieces. In effect, what we've demonstrated here is that a cake is 3-dimensional. Each of the 3 cuts is in a different dimension. One cut is really top down, the other cut is really left to right, and then side to side. The 3 cuts give us 8 slices, 8 equal pieces. And the reason, of course, is that 2 to the 3rd power is 8. So there's a case where visualization was important. Understanding about powers of 2 was also important. As long as we're talking about food, let's continue with another kind of cake. This is a cubic cake. You can see this is a cake that basically is been sliced or divided up into smaller cubes, 3 cubes on each side, on each face. Obviously, we have a total of 27 cubes. The cake is frosted on its top and its 4 sides. The bottom is not frosted. We are, like I said, we've created 27 small cubic pieces out of this cubic cake. The question that is asked is how many pieces are frosted in how many different ways? That is, how many sides are frosted? Well, what's the largest number of sides that could be frosted as you take one of these small 27 cubic pieces out? The answer is 3, because only a maximum of 3 sides can be seen on any one of the smaller cubes. The other sides are really on the interior of the cake. And here you see a picture of a cubic piece of cake that has been frosted on 3 sides. Where are these 3 sides located? Looking at the cake, we could see the only place where you would actually see all 3 sides of a piece are at the corners at the top. So 1, 2, 3, 4 corners at the top. There'd be 4 pieces that would have their 3 sides frosted. Okay? The next visual shows us a piece with 2 sides frosted. And the question now is, where are those sides located? And you can see in the next graphic exactly where those sides are. The sides that have 2, I should say I said side, the cubes that have 2 sides frosted. Excuse me. Again, the cubes, the small cubes that have 2 sides frosted. And if you count, you will see there are 12 pieces, 12 cubic pieces that have exactly 2 sides frosted. Okay? Next, we have pieces that have 1 side frosted. Where are those? Well, as we see in the graphic, they're located at the very bottom, in the middle, and the very center of all the faces. And also at the very top, the centerpiece in the top of the cake. There are a total of 9 pieces that have exactly exactly one side frosted. So let's see, we had 4 pieces that were frosted on 3 sides, 12 pieces that were frosted on 2 sides, and 9 pieces that were frosted on 1 side. That's a total of 25 pieces. The question now is, where are the missing 2 pieces? Well, what you must consider when you visualize is that there are pieces, obviously 2 of them, that have no sides frosted. These are 2 pieces in the interior of the cake, the one right in the middle of the cubic cake and the one below it that has no outside. There's no surface of that. Those 2 pieces are on the outside of the cake. And obviously 25 plus 2 would give us 27. So by visualizing and examining cases, we can solve the problem. Again, none of these problems are of great significance. The key thing is to take simple problems and to show you the power of organized techniques and then using the appropriate mathematics to solve the problem. Okay, I'd like to take a look at now is a couple of problems, and we'll work those at the whiteboard. And these are problems that I believe will demonstrate not only problem-solving techniques, good mathematics, but interesting enough, show that mathematics and knowledge of mathematics help make you a better consumer. The first has to do with pizzas. As indicated earlier, I really love pizza, one of my favorite foods. And many years ago, my wife and I frequented a pizza restaurant that had something very interesting. As you walked in, they had the pizza trays, the pizzas came on, nailed to the wall. So you could see exactly what the pizzas looked like, how big a pizza was. And basically they sold 2 types of pizzas. They had an 8-inch pizza and a 16-inch pizza. And they had the prices indicated. So we have an 8-inch pizza, and the 8-inch pizza cost $5. This was a few years ago. Pizza was a lot less expensive. They also had a large 16-inch pizza, and the 16-inch pizza cost $10. Now I want you to stop and think and determine which pizza is a better deal. Is the 8-inch pizza for $5 or the 16-inch pizza for $10 a better deal? And again, you want to eat as much pizza as you'd like. So it's not that you don't want the smaller size pizza because it's smaller. You want to know which one is the better deal. Stop the tape and consider the problem and come up with an answer. I would imagine that many of you said it makes no difference. I can buy 2 8-inch pizzas for $5 each, that'd be $10, or a 16-inch pizza, since 2 times 8 is 16. Now this would be okay if you promise to only eat along one diameter of each pizza. Because you see the measurements, 8 inches and 16 inches, are distance measurements, and those are the measurements of the diameter of the circular tray that the pizza is served on. We generally don't eat across the diameter. We eat the entire pizza. What we need to do is compare the areas of the pizza. And therefore, if we don't know about area and don't know the formula for the area of a circle, we're kind of stuck with believing whatever we're told. Remember that the area for a circle is pi times the radius squared. Now, what's the radius of an 8-inch pizza? Well, 8 inches in diameter, the radius is half of 8, which is 4 inches. We square 4 inches, we get 16, and we'll just leave pi alone. So we'll call that the area of the $5 pizza is 16 pi. Now, since pi is about 3.14, that would be around 50 square inches. Okay? Pi r squared for the 16-inch pizza would be pi times 8 squared. Remember, 8 would be half of 16. 8 squared is 64, so the area of the larger pizza is 64 pi, or about 200 square inches of pizza. Now we can see that indeed the 16-inch pizza was 4 times the area of the 8-inch pizza. It would take 4 $5 pizzas to equal the amount of pizza in a 16-inch $10 pizza. So if you said they were about the same, and therefore why not buy two 8-inch pizzas, you got ripped. Failure to know mathematics will cost you money. Another example, another food example, but this time from the cereal area of your grocery store. Let's take a typical cereal box. A cereal box is shaped as a rectangular prism or a rectangular solid or a box. And let's say we had this box, and we'll draw a little rectangular solid here. And let's say that this box was 6 inches across, 3 inches deep, and 12 inches high. What I'd like you to do first is to find the volume of that box. We talked about the volume of a rectangular solid. So stop the clock and compute the volume of that box. The volume of this box of cereal is simply 12 times 6 times 3, or a total of 216 cubic inches. Now, we know that 216, we should remember that 216 is a cubic number. It is 6 cubed, which means we could have a box that was 6 by 6 by 6, a cubic box, 6 by 6 by 6, and it would have the same volume. Now, each of these boxes have 6 faces. What we want to do is find the surface area, the amount of cardboard that is used to construct the box. The rectangular box at the top obviously has two pieces front and back that are 12 by 6. The two sides are 3 by 12. And there's 2 of them, so 2 times 3 by 12. And the top and bottom, of course, are 3 by 6, so 2 times 3 times 6. The cubic box has 6 square faces, all of which are 6 by 6. So there's 6 times 6 times 6. The surface area is also 216, but it's 216 square inches. I'd like you to stop the tape and compute the total area, surface area, for the rectangular box. Do that multiplication and addition now, please. Two times 12 times 6, well, that's the same as 12 times 12. That's 144 square inches. 2 times 3 times 12 is 6 times 12. That's 72 square inches. 2 times 3 times 6 is the same as 6 times 6. That's 36 square inches. And we add that up, we get 252 square inches. Now the question is this. If you were manufacturing cereal, would you want to spend the additional money for 36 more square inches of cereal? I'm not sure if I would, but they do, and that's the amazing thing. That's the amazing thing here, is that the cereal companies actually could have cubic boxes and save 36 square inches of cardboard multiplied by millions of boxes of cereal. But of course, they are solving a different problem. They are solving the problem of how to sell the cereal. And of course, the rectangular box makes the box look bigger, as well as small hands probably couldn't grasp a cubic box. But the whole idea of knowing about volume and area presents an interesting consumer question to us. We've looked at various types of problem-solving techniques. Certainly not all types of techniques, but hopefully you've gained some insight into organizing yourself to solve problems and using your knowledge of mathematics to help you solve those problems. In our next lesson, number 29, we'll talk about solving simple algebraic equations.